Okay, so our topic today is diffusion of information, social contagion. So we'll actually move slowly from the diffusion or from infectious diseases into actually propagation of information. And there are several topics we'll touch upon today. We'll talk about various rumor spreading models. And among them, there is sort of what's called homogeneous approximation and mean field model. And one thing I want to emphasize here that though we're going to apply this to approximation to a very particular model of rumor spreading, this approximation could be as well applied to all the epidemic models we talked about on the previous lectures. And then we'll look a little bit at the propagation tree, or the way there's a cascade, the way things spread on the network, and look at a few examples. So today I'll be talking a lot about examples from literature and less about theory. And the reason is because if you compare this to the case where we talked about epidemics, in epidemics modeling, there is sort of well-established set of models everybody knows about and everybody talks about and uses, like SI, SIR, SIS model. In the case of information propagation, or like rumor spreading, in this case, there is really no sort of generally accepted models. There are a bunch of models, and the modeling of rumor spreading goes back to 50s or 60s, but still there is no sort of one unique model that generally accepted to be a very good explanation for things. And so in some sense, it's definitely a work in progress, and it's a definitely place where you can actually try and come up with your own model, and maybe it will be as good as other model known today. So first of all, just sort of a quick definition, as much as you can define things here, that by social contagion, right, we mean some phenomena where or a process, various processes that talks about sort of individual propensity to adopt and diffuse knowledge, ideas, information. So the idea here, and the point here, is that it's really like real viral contagion, like viruses, like diseases, in the sense that people who get the information or who getting the new knowledge, in some sense, in this process, they do not have to make any decisions about getting that. It is, in this sense, is like it is like a virus. So you're being told this, and you already know it, whether you wanted to know this or you didn't. So, and that's sort of the rumor process. Next time, we will talk about very, very different mechanism where where a person actually has to make a decision to do something, all right? Something where it's more like sort of an influence-like. And there is the qualitative and of course quantitative difference in these two processes. So again, in the sense that the social contagion is about getting information just spread, and you got infected by the rumor or by the knowledge without even sort of any effort on your side or your concern. So you cannot refuse, in this sense. You cannot block this rumor from you in these models. Okay, so if somebody, it models exactly like an infectious disease. If you're in contact with an infected person, well, you're going to get it with some probability, right? And so you cannot control whether you're going to get it or not. So in this sense, the actor, that the recipient of the rumor, is passive in this case. And in some sense, it's very simple to think about the mapping of one of the epidemiological models into the sort of rumor propagation, right? So, for example, when we looked at SIR, well, first of all, we had like 3 models, right? SI, SIS, and SIR. So in SI model, you will have susceptible and infected. And at the end, you have everybody infected, right? SIS, there is sort of there is a loop. SIR, you have susceptible, infected, and recovered. And so SIR model, in this sense, is the easiest map from this epidemiological models into the social contagion model. So you can sort of think about it the following way. So the susceptible person, it's some individual has a new information, right? I'm sorry, who has not learned the new information. So somebody who doesn't know the rumor yet, all right? So he's in a sense innocent, right? There is an infected person, so somebody who spreads the information, right? The carrier of this rumor. And then there is a recovered person, and here, well, there are various ways you can think about it. But for example, it's someone who is aware of information, so he already was infected, he already had the rumor, but he's no longer spreading it. It's not interesting anymore to him, or by whatever reason. And so in this sense, you can actually think and map the rumor spreading exactly into this SIR, for example, into SIR model. Say, typically in this process, there are 2 main questions that are of interest. First of all is how far the rumor will reach, right? Or what percentile of all people in the population will be covered by that rumor. So speaking of epidemics, I mean of epidemiological models, the question is, are we going to have an epidemics, which means majority of the people will get the rumor or not. And the second question is how fast this infection spreads, how fast the rumor spreads. And it's very clear that say if we were considering a model like SI model, where there is, if you remember, it's only infected, susceptible people who become infected people, right? And there is no sort of way back. In that model, eventually, everybody in the population will get infected. So in this sense, everybody will learn the rumor and will be a spreader of the rumor. So, and we talked about this, that if you have a graph, then SI model will just cover the entire connected component where the rumor started. And so in this case, it's obvious the coverage, the size of infection, but depending on connectivity of the graph, there might be different rate of infection, might take different time to cover. In other models like SIR models, if you remember, we always talked about, and we looked at, for example, graphs for a number of infected people, and we got something like that if it's in epidemics. And we looked at the graphs of number of recovered people, or in this case, people who has information but no longer spreading it, and the curves look like that. And today, actually, you will be, you will build those curves yourself in the lab time. But the point is, depending on a bunch of factors, and in particular the ratio of the intensity of of infections versus recovery, when the time goes to infinity, right, you will have different values of the fraction of the population that eventually got infected. And in this sense, this is a reach, so of how far rumor went. Now, though this is okay, sorry. So the simplest way to talk about rumors is just using SIR model. But at the same time, there is somewhat different local mechanics in spreading rumors. And we'll look today at a few models that actually build on the same idea as epidemiological models, but they use somewhat different processes, and that leads to different results. If you remember, the key result from SIR model or SIS model is that there exists a threshold, right? And the threshold that if it is greater than 1, right, the ratio of beta to gamma greater than 1, then the rumor, then there is an epidemics, and the rumor covers everything. And if we have the threshold, if we're below the threshold, the infection will decay, and there will be very, very small number of people who actually got infected. Well, in the model we're going to see in a minute, it is different from that. One more sort of introductory word is the following. This whole sort of, well, science about rumors or information propagation, it's really this sort of mix of social sciences, a little bit of statistical physics, a little bit of computer science, and because the ideas coming from so many fields, there is really not very well defined. There's no very well defined terminology, and sometimes people name the same things differently. Sometimes they use some separate authors use their own sort of naming for effects and phenomenon, and sometimes some misleading terminology got accepted and adopted in the field. And what I mean here is in fact the sort of the term by itself, the social diffusion. Though it sounds very scientific and somewhat intuitive if you understand by diffusion the spread of information. If you sort of project back onto our first lecture, you remember that there is a process of physical diffusion on graph, right? And there is a process of physical diffusion, and it is very, very different. And it's very different from social diffusion. It's very different from sort of information propagation. Now, the reason is that in the physical diffusion process, there are conservation laws present. And what it means is, when we talk about physical diffusion, think about a droplet of water, a droplet of ink in the water, or like we talked, something on the graph, spreading on the graph. There is some amount of whatever material that spreads, and eventually the concentration of that ink will be equal through the entire volume, but it will be lower, much lower than the concentration of the ink in the original droplet. So it pretty much means that the amount of ink will just spread around, right, and in the volume. So, but the amount of ink will stay the same, and that means there's a conservation of mass. In the social diffusion or infection diseases, there is no conservation, in the sense that if somebody has a disease and this disease spreads to to its neighbors, it doesn't mean that the amount of disease decreased for that person. But that's what's happening when you have like physical diffusion, right? So if there is an ink and it spreads around, well, then the amount of ink in that point will decrease. In this sense, the information spread or infection spread is not physical process. There is no conservation of entity, right? It's not the physical substance that spreads, but informational substance. And so, we're gonna refer, as many other people, to the process of spread of information as a social diffusion, because it's sort of it's used in the field. But you have to remember that social diffusion has nothing to do with physical diffusion process, okay? And the equations we used in the very first lecture are not applicable here. Those equations are based on the assumption that there is a conservation of matter. And one of the equations when you actually calculate that Laplace system is the equation that tells you the amount of flow from the unit is equal to the decreasing of the mass in that region, and that's not happening in social diffusion. Okay, so that was just a long discussion, but I think important to understand that the social diffusion is just the word for where the word diffusion is used to explain the spread of information, and it's not a physical process of diffusion. Okay, makes some sense? Okay, good. Okay, so let's take a look at the models, at a few models. We actually will follow this what's called Mikaelethon model, but these two models are very close, and as I said, that they're like 50 years old. So, but they're totally based out of the epidemic models. So first of all, we have, as with epidemic models, we have this compartmental fully mixed model. So the population is again divided into three sort of compartments, and there are three. There are a little bit different names here. So they defined I as ignorance. So people who do not know the rumor yet, right? So in the previous language, it would be susceptible people. Then there is spreaders, those that actually spread the rumor. And finally, there are stiflers. That these are the people who actually heard the rumor, used to spread it, but stopped spreading the rumor. And so the process of sort of moving people from one stage to another is that process. Now, aside from just the change of notation, there is also some very significant change in the process. And in here, where the difference come from. So rumors, of course, the same way as infection disease spreads by pairwise contact. And we do have here two parameters. Well, first parameter is the rate of ignorant spreader contacts. So the rate of this contact when the person is getting infected by a rumor. And there is another parameter alpha, which is the rate of the spreaders, spreader or spreader stifler contacts. And here is something different, something that we haven't had before. So we're talking about contacts within the spreader population, and we're talking about the contacts in between spreaders and stiflers. And so the idea here is the following. The person can get a rumor if he meets, if ignorant meets a spreader, right? So here is our ignorant meets a spreader, and with a rate of lambda, and this is a rate of exchange of information, we get two spreaders. Okay, so it's really just, this is a sort of the process of spreading. Now the interesting part comes here. The idea is the following: when a spreader meets a stifler, so when somebody who spreads a rumor meets someone who already had the rumor and already not interested in it, what happens is the person who was a spreader also becomes a stifler. And so we got two stiflers. So, the understanding or the explanation of this is the following. You keep telling the rumors, and then you reach the person who actually heard about it, knows this, and it's not interesting to him. And so, you're the person, you as a person who spreads the rumor you're getting discouraged and says, okay, well, fine. They know the rumor, I'm done with it. I'm not talking about this anymore. Okay? So that's sort of the idea. It is the fact that that spreader becomes stifler, so the spreader stops spreading the rumor when not just by itself, not spontaneously, like it was in epidemic models when people just recover, but because of meeting a person who already has this rumor and stopped spreading it. And the same story goes here. If the two people who both know the rumor meet, as a result, one of them stops spreading the rumor. So imagine that two people who actually both know the same gossip wants, to tell each other, and it happens that both of them know this thing. Now, in fact, there are multiple variants of this kind of interaction. There were some variants where they say, okay, they both stop spreading the rumor. And there are variants that says, okay, it's not the first person, but the second person. There is slight difference in how this is handled. Or it could be that, they both stay spreading the rumor. So all these little details actually changes equations. But the main change, the big change comes here, right? And also we'll look later on into the extension of this model where actually the person who spreads the rumor, just getting tired of doing that and without even talking to anybody, spontaneously stops spreading it. But the original model, if we look back into those guys, it actually consists of this sort of three processes. Okay, does this make sense? Sort of. Okay. So again, this is all very speculative, right? So you can actually speculate about this, and you can say, oh well, in fact, the rumor spreads, a different way, maybe. You need to add something that when the person who spreads the rumor, the ignorant, the stifler, all three of them meet together, and that when the rumor stops. And you can just take that your idea and write it as one of the equations here, and it will change the model. But you can actually calculate through the model and see what it does. But sort of the original approach is this. And we're going to talk about the first. We'll look at what's called homogeneous approximation, and the idea is the following. It's sort of, this approximation sits in between, totally compartmental model, as we looked at on the previous lecture, and sort of network model. Think about the case of the network that, say, looks like that, right? So we have a regular grid, and in a regular grid, every node has equal number of neighbors. Or in fact, this model can also work on Erdős-Rényi random graph, though it's the connectivity in that graph is random. If we look at distribution of node degrees, it is Poisson-like, and so there is very well-defined average, and there are majority of the nodes in the graph has that node degree, and there is just the sort of exponentially small tails. Now, this approximation is not going to work for power law graphs, but for these types of graphs, like like lattice or Erdős-Rényi random graph, this is reasonable approximation. So what you see here is just the expression of the previous models in the form of differential equations. Now, this exactly the same way as we did with epidemics. We write everything as a sort of fraction of the total population. And the idea is the following. So, for example, the number of ignorant people, those who do not know the rumor, is decreasing with the rate lambda. They decrease on the contact in between ignorant and those who spread information. And because every person here has 4 neighbors, that's where this average number of neighbors come into play, right? It's just average number of contacts. So the second equation also consists of, so the total number of spreaders, it increases because of the contacts with ignorant people, right? Again, the probability here is proportional to the fraction of ignorant people times the fraction of spreaders, and decreases due to people, spreading people becoming stiflers, so stop spreading. And again, because everybody can have only on average k contacts, k is there, and this means, what this says is, okay, the person has to be a spreader, and it can meet either a spreader or a stifler, somebody who doesn't spread anymore, and that will comes here with a minus sign, which means the decrease. And the third equation, the number of remember, we have this, in this case it's I, becomes ignorant, becomes spreaders, becomes stiflers. This grows because of that process, and typically, of course, we have the normalizing equation. So these are three differential equations, and because k average is just a number, in the case of the lattice here, we have k average equal to just 4, and for Erdős-Rényi graph, whatever, it was a bad color. So we have k equal to 4 is just a number. For Erdős-Rényi, it's also just a number, so it's a number. So it's no different from the equations we looked at previously. Now, the only sort of significant difference is, in this term, which is nonlinear with respect to s. We didn't have that before. But we still can actually solve it. Now, I'm not going through the solution of the equations. I'll just remind you that when we looked at SIR model, in order to solve those equations, we did some sort of simple tricks. We integrated one of the equations. We substituted we integrated this equation. We substituted into this equation. We used this equation to sort of get it to this particular state. And if you're interested in how to do this, I will give you a reference to the original paper where you can actually see the computations, or you can actually do it yourself. But the point is, the same way as with SIR system, we cannot entirely solve this, but what we can do is we can take a look at what happens as time goes to infinity. So we can watch what happens sort of at the long time, at the end of the process, and the idea that when we get, it's clear that eventually, as the same way as with SIR process, for example, the number of stiflers or people who had the rumor and stopped spreading, it will saturate, right? So I mean, time goes to infinity, we'll have the saturation of the process. And the question is, okay, how fast the saturation happens and on what sort of level? But it's clear that's going to happen. And so that really means that when time goes to infinity, the derivatives will go to 0. And based on that, we can actually simplify equations significantly. And if we define R infinity as a limit of R of t when time goes to infinity. So again, this is R of t, some sort of very generic shape, and we're looking at this horizontal part of the equation. Then you can show that this R infinity obeys the following equation. Now, this equation looks somewhat similar to the equations for random graphs and to epidemic models. It is actually very, very, very similar, but at the same time, it's also very different. In order to solve this equation, and here the unknown is R infinity, right? That's what we are after. We're trying to figure out, this height. So how big of epidemic is at the end. You know, if you think about this, and you cannot just solve this equation as is, but we can actually analyze and see when this equation has you know, has different solutions. So first of all, this equation always has solution. Which solution? Actually, guys, which solution does this equation always have? So R infinity. What? Zero, yeah. So R infinity equal to 0 always satisfies this equation, right? We got 0 on the left-hand side, we plug in 0, and we got here e to 0 is 1, 1 minus 1 is 0. So there is always a solution here. But to see if there is other solutions, we can actually just plot, you know, left-hand side and right-hand side. If we do this, you know, on the left we have a straight line diagonal, and the expression on the right, and this is as a function of R infinity, we're gonna look, can look, you know, either like this, and then there will be a non-zero solution, or, you know, can look like this, and then there is no non-zero solution. And so the question is, you know, when we transition from the curve being under the diagonal line to that, and that transition, of course, happens when those two curves touch at the origin, and touch at the origin really means that the derivatives here, d with respect to dr infinity, that they're equal, right? And that's pretty much it. We actually done that before. And so what you do is we differentiate this, right? And derivative from R infinity with respect to R infinity is 1. And it's clear that when this satisfied is when our blue curve, you know, crosses and goes above, and that means we're going to get non-zero R infinity solution. So we're going to get finite epidemics. And you remember, well, I hope you remember that when we solve these equations in SIR, for example, model, or SIR or SIS model, what condition did we get? Do you remember? There was a condition for the existence of non-zero solution. There was a condition for existence for epidemics that we pulled from that equation. Do you remember that condition? Quickly to previous lectures. No? Okay, well, actually that's the only thing you need to remember about epidemics, is the fact that there is a threshold, epidemic threshold, right? There was this sort of, we had, I think, beta and gamma parameters, and if that's greater than 1, then we have an epidemics, and if it's less than 1, we do not have an epidemics. And beta, back then, beta was the rate at which you know, the infection would spread, and gamma was the rate at which people would recover. And when it was greater than 1, we had an epidemics. When it was less than 1, there was no solution to this. So what's interesting and different in this model is if we take the derivative the way we did here, and we actually look at the threshold, because, you know, we differentiate this at 0, and we look at the threshold, here's what we get. But, you know, 1 cancels out, and the threshold pretty much tells you that this lambda over alpha has to be greater than 0. But they're always greater than 0, because they're rates with which infection spreads, right? That there are contact rates. And so what this means, in fact, that in this particular rumor spreading model, there is no threshold. And that means that it doesn't matter what the sort of the values of parameters are, you will always have an epidemics. Your rumor always spreads. Again, because we added this dynamic process here, and we added we added this coefficient right there, sort of this term, it makes life very, very different from just regular epidemics, and it removes the threshold, the epidemic threshold. Now, we should be skeptical, of course, because it's a model, and that's what happens within this model. So within this simple, rumor spreading model, there is no threshold. So in this model, there is no rumor epidemic threshold, which means any rumor, however weak the parameters are, it doesn't matter, the rumor will still cover the entire population. Versus the epidemic model where we had a threshold, and you need to have infection rate higher than the recovery rate. Here it's not required. Okay, so that's, does make sense? Okay. Now, this is again very, very simplified model. Another way to deal with this type of equations is a little bit more complicated model. Now, here I'm showing you as it's what's called mean field theory. I'm showing you as a theory is applied to the rumor equations, but in fact we could easily apply the same theory to SIR model or any model we did before. Now the idea is the following. I mean, the mean field comes from physics, and so I'll try to explain the idea using the language of physicists. So the idea is the following: that let's say you have a bunch of particles. Okay, think about electrons, whatever, or think about lots of little masses. Okay, and every particle interacts with every other particle. And again, you can think about this as elementary particles, and there is they can be charged, and then there is a Coulomb attraction or repulsion, and they can have mass, and so there is you can think about the gravitational force. Doesn't matter. The point is you have a big ensemble, lots of particles in each of them, and they interact with each other. Okay. So if you think about this, if you think about graph representation of this, this will be completely, it will be complete graph, right? Every sort of particle interacts with every other particle. And in order to solve the behavior of this system, you need to write equations for, that takes into account interaction of every particle with every other particle. Okay, and that's lots and lots of work. So what physicists came up with is the following sort of approximate idea. Instead of actually taking into account all those interactions, let's think about the following. Let's take out one particle and replace the interaction of this particle with the rest of the particles by interaction of this particle with the mean or average field of those particles. And when you calculate for another particle, it's again this mean field and this particle. So instead of going through all pairwise interaction, you average out the action of everybody else as a mean field or average interaction. Okay, that's sort of the big picture. And so based on that idea, the previous equations can be rewritten. And so the only thing that is done here, and let me just show you explicitly. Notice here, for example, we're talking about di dt, and let me get some other color. Actually, I think I can erase it. No. Okay, as I can. All right. So in here, we have di dt, and we have I, and we have S. And if I wanted to convert this into interaction between each and every particle, well, I'll have to put some index for every node. I don't want to do this. What I want to do is the following. First of all, I want to calculate it. I want to group nodes based on their node degree. Okay, because in a graph we have nodes of different degrees, and we have this is a histogram that tells me that we have that many nodes of degree k average, and there is this many nodes with degree a little bit less than k average and less, and there is nodes with degree above k average, but we do know how many nodes of each and every degree is. And so what I want to do is I'll write an equation. I'll write those equations for every type, for every number, for nodes with different number of connections. So we'll have this equation for nodes that has k equal to 1, only one neighbor. I'll have the equations for nodes that have only 2 neighbors. I'll have the separate system of the separate equation for nodes with 3 neighbors. So it's not a separate equation per node. It's a separate equation for equivalent nodes in the sense of the number of neighbors. So one equation for all the nodes with 3 neighbors, one equation for all the nodes with 2 neighbors, one equation for all the nodes with 1 neighbor, etc., etc. And that's what this index, little index case here means. It means it's just for the node types that have k neighbors. And this term actually acts as this averaging over. And what this says is, the node that has k neighbors is actually within the mean field or field's interaction of all other nodes. In this case, it's sort of summing over all possible values of k that exist in the system. I'll not go into the details why we do it, sort of why we put this particular term in here, though this actually comes from the sort of probability distribution of the number of the node degree of the neighbor. But if you look at this system of equation, and again going back to the sort of original system, you realize that the only thing we have done is we replaced all these guys with corresponding summation. But as a result, if we can solve the system, we can get the behavior or the infectious behavior for the groups of nodes of different node degrees. So just pure intuitively, without sort of solving anything, which nodes do you think will get infected sooner? Those that have high degrees or those that have lower degrees, node degrees? So if we have a large graph and there are nodes of different degrees, which means nodes that have different number of neighbors, and there is a rumor spreading process in this network, which nodes will get let's say we have 2 nodes. One node has 10 neighbors and another node has 5 neighbors. Which of those 2 will most likely get infected first, or will learn the rumor first? 5 or 10? 10. Why?
Because he's more likely to have neighbors who have already contracted that rumor.
Because it does have many more ways to reach it, right? There are many more neighbors, so there are many more sort of routes to reach that node. And you can also analyze, and that's what sort of the solution of this system, if we do it based on this sort of k, will give to us. It will give us different infection curves for nodes of different node degrees. So it's still not as good as solving it per every node. It will solve it per every node degree, right, per every type of node. Now, well, you have to solve this numerically. And, if you solve it, here is what, for example, is done. And again, I want to point out, this is a paper by Morena, 2004, right? So though the original, the original ideas on the rumor spread came out, in 60s, it's 2004 when people actually start modeling this on the networks. So it's very recent. So what we have here is R of t, which is the density of stiflers as a function of time. Okay, so this is the sort of the traditional infection curve. And interestingly enough, it's not very different from those infection curves we have seen from SIR model. Now, we look here at the different at the different parameters. For example, parameter alpha, alpha, right? So we had two parameters here. Parameter lambda that gives you how often people, how often ignorant people and spreaders meet, and parameter alpha tells you how often it is spreader plus spreader, or spreader plus stifler, how often they meet. And what we see here, that this is alpha is 1, and this is alpha is 0.1 for the top curve. So what we see here is, if there is a lot of meetings, type of S plus S or S plus R, the curve goes lower, and we don't get a lot of people infected. Very quickly, infection dies out. If alpha goes to 0.1, well, the curve goes up. So you can just calculate this, right? And here on the instant, we have the same story, but with a number of actually spreaders. What's probably more interesting is a picture on the right, where different curves correspond to different values of k. And if you notice from right to left, this is the curve. Oops. This is the curve. The first curve is for k equal 3, and this is the curve for k equal to 80. And so, if the node degree is higher, right, then for that type of node, for the node with that degree, the infection curves goes faster, so the infection spreads faster to that curve, to that node, and in general, there is high probability that the node will be infected, versus the node with a low degree, which is on this side. And we get, based again, these curves are obtained by solving this type of system for different number of k's. So k1, k2, k3, and obviously they had a k equal to 80. So there was an equation here that had the node degree to 80. Okay, so in some sense, this is very, very similar to epidemic model. Well, because it is in that type of modeling, in that type of process. Now, what's interesting in that modeling is that you can actually modify the parameters easily here. And for example, you can add sort of intuitive or intuitive process of actually spreader just ceasing spreading a rumor by itself. So something that I think quite obvious, but by whatever reason it was not used in the original model. Remember, in the original model, there were two sort of processes, right? There was a process when a spreader contacts an ignorant person, and ignorant becomes a spreader. There is the parameter alpha, and the spreader contacts another spreader, I'm sorry, another spreader or Stifler parameter alpha. Sorry, the first one was lambda, the second one was alpha. But there is this third process, which is very, very similar to SIR, where people just, recover after some time. This is the same idea, that spreader after some time spontaneously can stop spreading. And you can just modify those equations and add one more term to those equations that will take this into account. And modeling this process, the authors actually found that in this case, if we have homogeneous networks and random graphs, we again have a threshold. And in this case, the epidemic will happen only if the ratio of lambda, which is the ratio with which things spread, to delta, which is the ratio with which there is a spontaneous sort of stop or spreading of the rumor by a person. If it's greater than these parameters, and k is an average node degree, and k squared is average of the squared of the node degree in the graph. So, and that's why that's what I meant that by saying that though the original sort of model tells you that when you have rumors spreading, that there is no threshold. You just take a little bit more complex model, more intricate model, and all of a sudden, you again get this threshold. Now, the interesting part here is that this really works for homogeneous networks, which means sort of lattices, or for random graphs. If we take a scale-free network and the scale-free network of the large size, this threshold vanishes. Now, why that happens? Do you remember when we looked at the power law graphs and we said, okay, P of k is, let's say, 1 over k cubed, right? This is sort of typical power law graph. Do you remember if we calculate k squared, what is it equal to? What is average of, what the fluctuation or average of k squared in a power law graph equal to? Now, if we want to calculate this, how would we do that? Well, this would be an integral of P of k, well, all right, let me write it here. K squared will be an integral of P of k dk from k min to infinity. And if I substitute here 1 over k cubed, I'll get 1 over k squared, because one of the k's cancels. And if I take an integral, it will be log k, which actually diverges on the upper limit. And so what this actually means is that for scale-free network, this goes to infinity. And that means the threshold goes to 0. Okay, so one more time. The formula here works for both, for pretty much for any type of graphs, whether it's homogeneous, random graphs, or scale-free networks. This is a formula. This is a threshold. But for the scale-free networks, because they have huge oscillations, oscillations in node degrees. When scaled-free network growth, the average of k squared diverges, and so this thing goes to 0. Okay, because of the large variances for k squared. Again, we did these calculations previously. If you take power law degree distribution, calculate average of k squared, that diverges. And so that means this limit goes to, that threshold goes to 0. Anyway, so by adding and modifying the model and adding this, you know, spontaneous stop in a rumor spreading, the researchers showed that on one hand, for homogeneous and random graphs, we sort of restored epidemic threshold, and you need to have sort of higher rates of infection than the rate of spontaneous sort of recovery. But in scale-free networks, there is still no threshold. And so in scale-free networks, you'll always get the propagation of rumor of the entire network. And again, since we know that most of the networks you know, we deal with social networks, they are scale-free networks. So we again sort of at the point where seems like rumors can spread over the entire network. Well, and here, of course, we're talking about connected component, right? So over the entire connected component of the network. And you know, here is just sort of a few pictures based on the equations that the authors solved. That show to us, on one hand, this is the case for the random graph. So this is a random graph, and you see now here we have the scale of, or the size of epidemics. And when we're below the threshold, in this case, when lambda is small, the epidemics does not spread a lot. And then, you know, this is the size of infected component. It starts growing, right? And depending on sort of other parameter, you know, it can grows with a different speed. And so this is very typical this is like SIR model. But what it also shows that when you have a scale-free network and getting pretty large graph, this threshold slowly moves towards 0, and actually, you know, right here there is a non-zero derivative that tells you that there is a phase transition and there is a strong change of behavior. Here it smoothly goes to 0. So it's very, very different behavior, and that's what allows, you know, plus theory allows to project that when you grow the network significantly, there is no threshold in scale-free graphs. And here there is sort of on the same modeling, there is a comparison of how infection happens again on a regular network versus, I'm sorry, on a random network versus a scale-free network. And how on a scale-free network, if you look at this, you know, the infection, or you know, the rate number of people that are spreaders grows much faster than what we get for scale-free network. I'm sorry, that's what we get for Poisson network. Now, if we want to compare two different types of networks, like random graph and scale-free network, you know, we need somehow to make them, you know, somewhat comparable, right? How would you select the parameters to make them comparable? Is it clear what I'm asking about? You know, we want to study different type of networks. You know, we in some sense it would be good to compare apples to apples, oranges to oranges. It would make sense to run experiments on a very, very different networks, right? Something should be very similar in those two networks. So what can we make similar on those networks? I mean, we can you know, we can look at the networks with the same number of nodes. Can we? Yeah, we can look at the networks with the same number of edges. That's possible. We can look at the networks with the same density, which is the ratio of the number of edges to the maximum number of edges. Typically, and in particular, what these authors did, they fixed the average node degree. The average node degree of the network. And the average node degree, if you remember, it's connected to you know, to the number of nodes and the number of edges. So it is similar to network density. So both networks that considered here as a comparison, they have the same average node degree. And that, then it's sort of, at least you can compare them. The result is what we suspected from the very beginning, that when you have a scale-free networks, rumors in a scale-free networks spreads much faster, right? And they will cover bigger part of the network than if we deal with sort of random graph models. So the result is we have faster spread, right? Faster epidemic spread and larger coverage. And so in this sense, the scale-free networks are sort of well designed to spread rumors. And intuition behind this is the following. On one hand, the scale-free networks, we know they do have a lot of local triangulation that allows you the rumor to spread in the local neighborhood. But at the same time, they have long-range connections that allows information to travel fast, far away from the source. And those two properties, create this advantage for the scale-free network in terms of spread of rumors. So, that's sort of the overview of those models. So without going into the details of equations, I understand that it's very hard to look at the equations and understand them, especially when they're just shown here on a slide. What I want to make sure is that you guys sort of got the idea, the flavor of these models.
Question is about how does the spread of the rumor depends on which nodes are initially infected.
Okay, very good question. In these studies, for example, I believe in this simple model, the higher the node degree the density is trivial for this simple model. The higher the node degree, the further the rumor spreads. We will look at somewhat different models next time, the models that deals with situation when somebody needs to make certain decisions. Over there, the answer will not be so obvious. In these simple models, it is the nodes with high node degree that will allow you to spread rumor, faster and further. Now, one more reason why I sort of showed you all those pictures is because we are actually approaching the first project. Okay, we'll formulate several topics for you guys to work on. But the idea of what we have in mind is that you actually will, investigate one of these models on some of the graphs. And one of the questions you can sort of pose for yourself is, okay, within this model and this type of graph, what nodes, how can we select the nodes that we need to infect to make the epidemic or to make the rumors spread quicker or cover the more sort of larger areas. And node selections can be based on node degree or other metrics. Remember, we had like various centrality metrics we talked about, like between the centrality, we talked about page rank, we talked about other things. Maybe if you select nodes based on those metrics, they will be more efficient as their rumor spreaders, or maybe not. Okay, so but that's up to you, up to sort of solve when we try to solve this problem. One more comment here is we could have okay, I gotta slide back for a sec. When we looked at this original equations, and this looks like a mess, but when we looked at these equations, we could actually do the same thing as we did with epidemic modeling. And we could rewrite those equations in a matrix form. We could say, okay, well, let's write, so what I done here is I moved from this equation from the sort of compartmental model to equations per node degree. We could have moved from here and write equations per actual node, and there will be more equations, and we'll have everywhere the connectivity matrix, and then we could have solved them the same way as we solved equations for epidemic models. And this is one of the one of the ways to model things. And I think Andre will talk a little bit more about this on the seminar today. So there is nothing special about that. Okay, so for the rest of the lecture, we'll actually look at a few more models. Oh, before we go there, this is like, I really like this paper. I mean, I didn't like that much the science behind it, but I really like the data and the results. This is really cool. In general, when you look at the spread of epidemic, spread of news, spread of ideas, it's quite hard to trace them. You know, how the spread is actually happening. And these guys, they come up, I think, with a brilliant idea. So there is a famous technique in theoretical physics, which is called Fineman diagrams. Well, Fineman, Nobel Prize winner in late 40s, he came up with a way to sort of write complicated equations that are used in quantum field theory as diagrams that significantly simplifies derivations. And so just to give you an idea, like, if you have like, multiple, integral, then to calculate the interaction of the particles, Feynman proposed to draw it as, say, some sort of diagrams. So replacing, there was like electrons, positrons, etc. So replacing actual integrals with diagrams. And that significantly simplifies everything. Significantly simplifies notations, and you were able, and he proposed operations with those diagrams, and sort of, every node on that diagram has physical sense, and you can add them up, etc., etc. The point is, this is a very distinct technique of how to deal with complicated equations. And he proposed it in the late 40s, and it took off. And if you look at this, this is a number of authors in the papers published at that time that actually use that technique. All right? And this is really an adoption curve for this new method of solving equations. Here is US and Japan, right? So these are authors from the United States and Japan, and this is how, with years, the adoption grows. And with Japan, it kind of starts saturating at some moment. Here, it just, in US, just keep growing. Now, this picture is Soviet Union. First of all, notice delay. Here's the result of Cold War, embargo, everything else. Russian science, that many years. I think this is like 1948, when Feynman published his original research paper. Oh, and I have to say that these days, everybody who is in theoretical physics does quantum field theory, they use Feynman diagrams. So that was happened, because of the isolation of the Soviet Union. Now, there is another story here about this slow curve, slow startup, is because Russian science had extremely strong school on its own, Landau School of Physics, and Landau himself, was not a big fan at first of Feynman diagrams, and so there was also resistance from the from scientific community in Russia. But eventually, it became obvious that this is the way to do things, and finally, the adoption also took off in Russia. So this is actually an incredible graph of the spread of the idea. And the reason it could be done is just because, guys simply sit down and analyze the papers published back then in the field, and just looked at what techniques were used to solve the equations, whether it's just done by integrals or, and I'll give you references to this. But anyway, this was a collection. This is the data. I mean, the data is amazing. And the authors of the paper, they said, okay, well, in order to try to match this data, we're going to do, even more complicated system of equations. I'm not going to go through each and every term in here, but the idea is that they, in order to sort of match those curves, they had to come up and introduce two different type of exposed of those infected people, those who are actually know and support, and those that know but sort of resist the spread. Okay, and the result, there was like the model got like 9 different parameters. There's 4 initial conditions, but you can actually take the model, you have a data, and you can calculate the parameters from the data to the model to get a descriptive. And here on the right, you got the lines. Those lines comes from actually the model. And so this is number of authors that are using the technique. So instead of say this curve, we got somewhat different curves, but you can still sort of get those curves based on the model. Now, the reason why I don't like, I really love the data and the idea. I'm a little skeptical about the approach, because it's clear that if you make a very complicated model with lots of parameters, you can eventually match any curve you want, right? It's in some sense, it's like in machine learning, right? The question of parameter feeding, the idea of generalization, and this could as well be like just simple overfitting. But anyway, what this shows is that the reason I wanted to show you, well, first of all, is because of this amazing proof of the Cold War and the isolation, and because this also shows you that you can just take those equations and really play around with them, create your own sort of equations at your own type of infected or people who are susceptible, or whatever you want to do. As long as you sort of follow the generic approach, you still can resolve this and build a model of it. Any questions about this? Yeah.
Is the approach to, for example, here we don't know how do a network of scientists in Russia or in USA, we don't know structure of these networks, but we can maybe estimate some parameters of it using dynamics of idea spreading.
You can actually even do easier than that. What you could do is you could look at, for example, co-authors in the papers, right? And if you have co-authors, it means people work together, and you can get you can get a graph of how people interact. Yeah, you're totally right. You can definitely make this model better by building the co-authorship graph, or you can also think about it as again, there are schools of science, right? There's Landau schools of science. It's well known who was his first students and who were students of his students, and so you can also build it that way. So you can definitely improve this model if there is a desire to do it. I'm not sure, but I hope this data is available. But anyway, this is actually a great example of, I'm sure there are other sort of data sets that you can come up with where you can sort of cleanly monitor how things spread in time. But the paper written by physicists, of course.
May I ask a question again, because maybe is the approach to, for example, sometimes network properties is unknown, but we know something about rumor spread. Is the approach to estimate some parameters of a network using dynamics of the rumor spread?
Yes, we will talk. We will not going to talk about it today. One of the last lectures in the course will be about prediction of edges in the graph, and that's pretty much one of the ways, one of the ways to do it would be if we look at their how information propagates and try to predict either other edges in the graph.
Because if we compare the slopes, for example, for USA and for USSR, the USSR slope is a bit steeper. No, the USSR slope is less, and does it mean, for example, that the scientists' network is less dense, for example?
It could be actually, this could be a signature of the fact that in US the communications were much faster, right? And the network is denser, better connected than within the Russian science. That could very well be the case.
Okay.
So, but anyway, that's I think it's kind of a great example of how you can actually use data and look into into the history and the models. Okay, so we actually, if you have a few slides to cover today, a couple more things. What I want to talk about is somewhat not modeling, but really the details of propagation itself, right? And so, rumors, news, infection, it's all spreads over the edges. And in fact, this goes to your question, right? So we have the graph, and this we have a graph, and it's undirected graph. And let's say, there were rumors, and the rumors are shown here in green, or information, and it spreads over the network. And so on the left, we actually have the network and the rumor on top of it. And this is just the rumor itself. And what you were asking a second ago is like, okay, when we have this, can we reconstruct that? And the answer, yes, to some extent we could. Now, what's interesting, I'll try to show you on the next few slides, is that in real life, these events are quite rare. So in most cases, the propagation graph looks like a tree. So you rarely have those triangles in a propagation graph. You do have them, they do occur, but not very often. In most cases, it will be a tree. Now, there is no much theory left, until the end of the lecture. It's mostly examples. Now, when people talk about this, the process of propagation, sometimes they call them, cascade. And so when you hear like the cascade, it's usually meant this. So here's a bunch of cascades from Twitter, right? Each of them has to do with some big event. Now, what are these guys? Yeah, it's earthquake, right? Now, this is election in the United States. It's GOP, the Grand Old Party, which means Republicans. Now, what's this?
Egypt Revolution.
And this? Yeah. And there is one missing, which I'm sure we could collect. Yeah. Look at those pictures. Here, it's clear that there is a center. This is probably some media that tweeted to a lot of people. Well, people were concerned saving their lives, so they didn't retweet, right? But there were some retweets, and there were some people because they tried to cover as many more as many more people as possible. It's very different for the revolution and for uprising. So you can actually see the difference, and it's extremely different from the picture sort of relaxed tweeting and arguments, arguing when it happens, political discussions, right? So these are action tweets versus sort of discussion tweets, right? Picture. But the point is, in all of those cases, you do see like literally trees. You do not see a lot of sort of cross.
Yes. We have a question.
Yes.
Sorry, can you say a couple of words how to interpret this? The more blue is the color is more dense. The tweets, including this hashtag.
So what's here? Okay, actually, coloring I believe here is just for the visual effect. So what happens is the nodes are black and the edges are blue, and when you have this sort of dark here, this means just you have a lot of nodes, in that that has been retweeted from that particular person, and the edges are retweets. So it's somebody tweeted and other person retweeted it.
Thank you, because I didn't know how to interpret.
Right, and there are actually the picture is generated by really cool by really cool program that been developed by Indiana University, I think. Yes, University of Indiana, their research center, and if you're interested in this kind of stuff, I definitely recommend going to their website, because they have tons and tons and tons of pictures, Twitter pictures for different events in the world. So you can actually look at them, and for some of them you can actually get data. So, and these pictures are taken from this paper. Now, I want to remind you something that we've done, several lectures ago with trees. It's this sort of Galton-Watson branching process, right? The tree, the propagation of information on the tree. Now, the reason I'm looking at this is simply because, well, you just seen a bunch of those trees. And sort of keeping aside all the big signs of multiple equations, differential equations, etc., etc. For those trees and for the Galton-Watson process, we came up with a very, very simple formula. So, and the formula was the following: that if on the somehow I missed the entire slide. If at a node there is a probability P that the rumor or infection will be transmitted, and the node has K connections, then P times K actually gives you the mean number of infected, and if it's greater than 1, we'll get a cascade, and if it's less than 1, the rumor dies out. And so what it pretty much tells you that in order to estimate when you seed something with a rumor, and let's say you have your connectivity graph, you're a Twitter user and your followers, right? And you have say this is your followers graph in a Twitter. So people who actually you can tweet to. And when you send a tweet out, the question you should ask yourself is how many of your connections on average will retweet your tweet. So, if you have another connection and you know that he has 10 friends, and there is a probability 0.1 that he retweeted, it means, okay, your information will sort of keep going. And if somebody has 100 friends or listeners on Twitter, and there is a probability that that he will retweet is 10 to the minus 4th, well, it's a dead end. If somebody has only 5 connections, only 5 listeners, but he retweeted for sure, well, then infection will spread along that line. So the critical for understanding this is really knowing for every node in the follow graph how many edges it has, so how many people going to listen to this person, I mean, to how many people the information will flow, and knowing the probability that he will activate, that edge will be activated. So the probability that the person will listen. Does this make sense? So the reality is really, it's really the probability times the number of friends. That's pretty much all you need to know. Here is another experimental study. As I mentioned, the good data hard to come by, and though right now there are Twitter and there are Facebook data, there are quite a few researchers who are trying to analyze email communications, because that data is very clean in the sense that you can actually trace every step in there without losing anything. And this analysis of an email newsletter, where the idea was that there were a bunch of online advertisement with an offer to subscribe on some research newsletter, and there was explicit award to people for recommending this letter. And they started with 7,000 seeds. Eventually, they reached 30,000 people. But what they found out, that the majority of cascades in their case were pretty small. And this is one of the larger cascades they saw. So this is the person who started sending out that newsletter to his friends, and hear how this newsletter propagated. Notice there is really no loops, no triangles, no closed paths. It's just pure sort of tree spread. Now, if you calculate for this graph, on average, there is 2.96, the node degrees here are 2.96, and the way things has propagated, this infection probability is this one. So if you multiply this, it will be much less than 1. And of course, the infection died out. It didn't spread all over, the user or the internet or whatever. So, they had it's kind of interesting also paper. It's kind of disappointing paper in the sense that people expected that, in general, the effect of this, word of mouth is much stronger. But what they see is, lots and lots of small cascades, sort of small patterns that do not connect into a sort of global thing. And here is another research done pretty much the same year at Cornell. The idea was that looks also at the emails, and in this case, these are petitions that were going over the internet in 2002, 2003, trying to stop, war in Iraq, and sort of those petitions were asking people to sign them and also forward to friends. And because of their, explicit signature, you can trace back the whole history of the letter signing. In fact, those petitions collected around 20,000 signatures, but they were distributed in multiple chains. Now, but in this case, there was a big tree, like the largest tree. But the fact is, it was also kind of interesting structure, and we'll see it in a second. Majority of the nodes in this tree had very few connections, and so if you zoom in, that's what it looked like. So what it shows here is really that the person who gets the letter pretty much sends it to one person, and that person only to one person, that person only to one person, to one, right? It's only, for example, here when somebody sent it to multiple people, and those people sort of resended it further. So the majority of the sort of transactions were really chains, and that's why they call it chain letters. So that also tells you something about the way sort of information spreads in real life. And the models we looked at the beginning of the lecture cannot explain this. This behavior. so there was actually a lot of work here one can do on information propagation. Finally, this is like, I think, yeah, this is the last slide. This is another example. This is example from a large online retailer, and the idea is that after purchase, the purchaser could send recommendation to purchase this item to a friend, and there is even incentive, so you can get a referral for the credit. And still, you can see how sparse the graphs are, and you barely see any triangles or anything else. Now, this is a medical book. And this is for some Japanese graphic novel. So there are clearly some big fans of this stuff, but there are not that many of them. So it does look like in most of the cases that has been studied, the spread of information looks like a tree. Okay, and so you might sort of keep this in mind, that cascades are typically trees, and then the simplest model will do. So that's pretty much it for today. Next time we're going to talk about different process, the process of, well, what's called diffusion of innovation, or the situation when one needs not only sort of to hear the rumor, but to actually act upon it. And that there is so-called threshold models of collective behavior. And over there is a very interesting also interplay in between sort of getting the information, actually acting on it, interplay between structure and action on the network. But honestly, this whole story about information diffusion on the network is still a very much sort of open research, big research project. You can see a lot of different, a lot of people doing different type of research, looking at different models. So far, there is no sort of single consensus of what model best describes the process. And I will add references to the presentation a little later, so they will be available online. Any questions? Okay. All right. So just again, a quick reminder: we'll give you before the holidays. We'll give you the first assignment for the class. It will be about information propagation or rumor spreads or epidemic spreads on some real network. So you might also start thinking about where you're going to get data, what kind of data you're going to use for that project. Okay, done for today.
Thank you.